Okay, so I'm going to spend the first time of this webinar talking about ontologies. So an introduction, assuming that you know nothing about ontologies. So I will start from the very beginning, and then I will try to show you what we did in the first 6 months of the CoBrain project. So you may be a bit maybe out of your comfort zone at the beginning because we will start to talk about philosophy and so on. And but I would like to reassure you that in 6 months of CoBrain project, we are I would not say done in creating an ontology for thermal spring, but we are in a really good shape to finalize this task. So it may be a topic that you can find a bit outside of your expertise, but don't worry because it is quite easy to jump into in it. Especially if EMMC will help you in using these tools and to deliver something in this field as expected by the call. So let's start from the very beginning. So what is an ontology? So an ontology, the first starting to speak about ontology was Aristotle, in which in his metaphysics book, so the books that are placed in the shelf after physics, started to debate about the things in terms of their fundamental nature, in particular the existence and the properties of things. So that we can consider the ontology as a philosophical discipline that is a sub-branch of more general metaphysics. In fact, the etymology of the word ontology comes from the science, from ontos and logia, which means the science of being. So it should be in its definition the science of everything that exists. So, but philosophers in ancient Greece had not a lot of, I would say, science, knowledge of the world, except what is perceivable by senses. So they start to talk about, you know, tables, chairs, color, and whatever, and they started to develop the theory of everything, of beings, developed, for example, the theory of universals. So, for example, Plato was one of the most important philosopher, and started to separate the concepts and their instances. Aristotle, in categories, started to formalize in a more, I would say, pedantic way what things are and their properties, not without raising some objection, like for example the comment of Russell about Aristotle, in which that consider his work as common sense prejudice pedantically expressed, for example. So, but what we can identify in the ambition of this philosopher is that what they want to grasp is the absolute truth about things. So there are three ontological temptations when one approaches ontologies. The fact that you can imagine that it is possible to completely understand what things are, what are the properties, how to relate each other. You can imagine that this understanding is univocal, so everybody should agree on these things. You can imagine also that this knowledge is expressible, can be formalized, so that can be made accessible to others in an understandable and usable form. So these are the three ontological temptations, so and also ambition that lead people to work on this ontology field. So this would be a perfect ontology, but are these expectation promises achievable in practical experience? Well, the answer is no. In fact, if you follow the history of philosophy, you will see that from the assumption of an absolute perspective about things, so that you can find in the Plato or Aristotle work, we move in more modern times to an increased subjectivity, in which a philosopher start to understand, to identify the limits of the knowledge, and the observer is now the center of the epistemological endeavor of dealing with things. So even now in philosophy, what is an ontology is still an open debate. So if you navigate through the Stanford Encyclopedia of Philosophy, you can find a definition of ontologies, and this definition is essentially that is not so clear what the ontology field is about. It's not clear how to settle a question, and whatever. So it is. So it seems that the ontology approach is something that should be confined to philosophical debate, and even in this debate is something that has been, overruled by recent advancement. In fact, what we did, I say we because I assume that you are probably applied scientists or engineers, physicists, chemists, and so on. The practice decided to move on and to use mathematics as a way to physics and mathematics to deal about the nature of things. In fact, Galileo Galilei started to propose approach, an empirical approach to things. So there is no absolute truth. There are evidences come from observation. And now what we have now is mathematics. In fact, mathematics is the foundation of our scientific method, and it is the language that allows us not only to describe things, but also to predict things. In fact, we use modeling to predict how things behave. This is a huge achievement that went far more than give us far more than what an ontology for a philosopher it was expected to deliver us. In fact, today mathematics seems to be the one of the major disciplines upon which other disciplines are based, because it enables us to build model of the world, and it is somewhat computable. So the language is the key. So the possibility to say things about to say statement about things, and the possibility for this statement to be computed in some way. So the language is the key. So given that, there is also in the last century, several philosophers started to analyze the possibility to use the language of logic. For example, you can see a theory expressed in first order logic to express ontological truth. So let's try to use this language, so the logic as a language to express what things are, what are their relation, instead of using natural language. And let's see if this is computable in some way, if this is enable us to resurrect an ontological approach using a formal language. So this is something that has been debated and improved in the last century. But the ontology started to appear again on the bookshelf of engineers and scientists with at the beginning of this century, or starting in the 90s, but in the beginning of this century, where we start to develop the semantic web technologies. So in this way, in this framework, ontologies has been provided with a language that it is computable, and it is easier to deal with than first order logic. And I'm talking about the RDF, RDFS, and OWL languages that are a way to formalize knowledge using a computable language. So an ontology now possesses a language, which is in our case OWL, that has been a language that's been developed in the semantic web, that allows us to express statement about a domain of interest, so the things that we are interested on. And this an ontology is consists of 3 different syntactic categories. So the entities that can be classes, properties, or individual, and actions about these entities, and expression that describe the domain. So in this way, it is possible to say something formally about a domain in a way that can be also can be computed. It is a very trivial example about what an ontology is. You can see here what is called the T-box. With T-box, we intend the abstract knowledge in which, for example, we know that a flower, a color, and a car are things, and that and yellow and red are colors. So this is a taxonomy. Then we have the A box, in which we declare that exists something, for example, these 2 cars that are cars, so there are also things. And exists something like these colors, and we can provide relation between the colors and the entity, so that we can not only express in general how things should appear, but we can also express in particular how things appear following the conceptualization that is formalized in the T-box. So classes, relation, and individual are the what would make an ontology. And the real-world objects are the domain of interest. So are the things that we want to represent, things that are in our lab, these things that can be our devices or our equation or our software, for example. These are the things that we want to represent as individual in the ontology, and according to a knowledge formalization provided by the T-box of the ontology. This graphical representation can be serialized in RDF, so it can be expressed using in this case, this is a turtle based serialization, in which each statement about things is about technology formalized in terms of triplets. So subject, predicate, and object are the way in which we express a statement about things. And you can see here the fact that we can represent an ontology using a series of triples serialized, in this case in turtle, using the owl as a reference. So ontology is important because it can play the role of math for physics. Of course, is not so computable, and is not. It doesn't have powerful predictive capacity. But I think that this similitude can be applied, can be inferred from our experience. So an ontology is similar to math, is a universal language, so is transcend linguistic differences, is hard to learn because it requires adequate training. Both are able to perform logical reasoning. They provide both models for the world, and when they work, they can be hidden. So an ontology is not intended to be exposed to the final user. It's a tool to build something that works and provides us functionality. But another important thing is that this language, this realization of an ontology in RDF is something that can be understood by the machine. So so ontologies are the key to bridge the gap between humans and machine, because an ontology is somewhat a formalization of the knowledge of human beings, and when they are formalized symbolically, they can be integrated in other system, for example, by supporting AI, in order to improve the capability of digital system to infer, but also to interact with humans by understanding the knowledge that humans give to them, but also to deliver knowledge structured in a way that is compliant with an ontology, so that it is understandable by human beings. So, in fact, symbolic reasoning can be used to improve the capabilities of machine learning approach. So here there are some slides, but I don't want to go too much into that. But just to say that there are limits to machine learning, especially due to the complexity of the domain that they usually want to describe. A symbolic reasoning can provide a predefined set of knowledge that can be used to increase the capabilities of machine learning approaches. So, as I told you, an ontology is a representation of the world according to a conceptualization provided by a human being or a community of human beings that agree in formalizing the world, so the domain of interest, in a particular way. In fact, what the human beings are always the begin and the end of whatever we create. So if we create something, it's not because we like to build the devices, but because they are useful to us. So one of the roles of the ontology is to provide meaning to the input that we provide to a tool, and to provide meaning to the output of the tool that we created. So it is just like the von Neumann architecture, in which you have a computational unit, you have the memory, but always you need an interface, an input-output, because otherwise things would be a black box. And this input-output needs to be understandable by human beings. The problem is that there are several ways in which you can conceptualize the world. You can look at a thing and then use, for example, the chemistry language to describe it. Or you can use some ISO, or you can use a manufacturing vocabulary, and so on. So there are many ways to represent the world, and so one can question about the fact that there can be one and one only ontology to describe the world, but there should be more than one ontology to deal with the world according to different perspectives. In fact, this is what we realized. One of the things that we want to address with the EMMO ontology. So the fact that we want to accept a pluralistic way of the world. So the fact that there may be many different ways of knowing the same thing. So what we want to do in our ontology is to approach the fact that there may be a diversity of views. For example, we have the ISO 9000 and the ISO 40,000 that provide different definition of the concept of product, for example. So for one ISO, the product is that it is generally tangible. For this ISO, instead, a product can be tangible and intangible. So how can you provide an ontology? So how can you provide a univocal definition of product when you have two ISO that use the same label, so the same term product, into different ways? So it seems that this can jeopardize the ambition of ontology. In fact, if you create a taxonomy of product for these two ISOs, you have that these two taxonomies are different. A product for the 9000 is tangible, it is an output of something, and this output can be also a service, but if it is a service, it's not a product. while in the ISO 14,000, you have the product that can be a good or a service, for example. And so a product can be tangible or intangible. So as you can see, there are problems like that should be addressed when you want to create a univocal representation. And this is usually because we standards proliferate trying to solve this problem and trying to impose a unique way. So what we did in the EMMO ontology is to avoid this proliferation of standards, or to propose the EMMO as a new standard to express things. But we want to provide a way in which you can express your way of the world using a set of common fundamental concepts. Also, in physics, in applied sciences, we have different clashes definition, for example, of atom and molecule. For example, this is the taxonomy for a chemist. So molecular entity is an atom and a molecule is part atom. But for a physicist, maybe an atom is simply a subclass of a molecule, being a molecule, a nucleus surrounded by electrons. So an atom can be, the simplest case of a molecule. So how can we deal with this problem? So the idea in the MMO is, in our ontology, is that we want to create we want to host different vocabularies and to find the overlapping region, or the things that are not cannot live together, using a very fundamental approach. So the benefit of our ontology are the possibility to reason, to apply constraint to the data. So this is an example of a EMMO taxonomy, starting from the root. So reasoning about the knowledge. So you can, for example, if you deliver a data that it is semantically described using this concept provides you constraints. So you cannot say whatever you want about the data. So if you say something that is not coherent with the knowledge system, then the ontology will alert you that you are saying something that is not in line with a certain knowledge. We can infer also new knowledge. We can use ontology as interoperability, so we can express concepts that may be understood and shared between disciplines. So it will be easier to jump from one discipline to another if we have a shared view about what things are. And also it can provide you expressivity, because you can express the meaning of a data set in a much better way than using a simple keyword. Because usually what you do is probably find a vocabulary and then tag a data set with a set of keywords, without regarding a lot about the fact that these keywords are coherent, or what is their meaning when used outside a particular context. So the ontology provides you a background knowledge that is structured in a way that you can use it to reference as a reference for your data, and helps you to say something that it is consistent and not illogical. So the MMO is an ontology that we started to develop in 2018, and we to deal with materials and modeling. But now it went a bit further and started to be an ontology for everything. So since we are applied scientists, engineer, physicist, chemist, and so on, what we decided to do is to base our ontology on a very strong radical physicalistic approach. So we started to create a logical system in which everything can be decomposed up to the elementary particle level. So our logical system is something that helps you to navigate through the different levels in which things are in which elementary particle aggregates up to the macro level. So as you can see Here there is a picture showing the taxonomy of the EMMO and how this taxonomy goes to this fundamental taxonomy, which is the standard model of particles. So the EMMO, we have a fundamental basic foundation on the classes that represents the elementary particles. Then we also started to introduce in the ontology the physical phenomena that are admitted by the standard model of particles. So the interaction that comes from electromagnetic forces, gravitational forces, weak and strong nuclear interaction, and so on. So in this way, we created a causal system that can represent things using direct acyclic graph. So in the EMMO, things are represented as causal nodes that are connected using causal relation. And this is a fundamental axiom that made up the EMMO ontologies expressed in first order logic. I don't expect you to deal with that. This is something just to show you that we have a very strong logical foundation that are grounded on very hard science in order to be sure that what we say is consistent with the most fundamental model that we can apply to describe things. This is the fundamental taxonomy of the EMMO. You can see that an EMMO entity that is whose ambition is to describe all the entities that you have in the world can be item of collection. Item are things that are physically related. So there is a physical interaction between the elementary part of this entity. Here, the collection is a collection of scattered, non-physically related entities. We focus on item, and then we define the quantum entity, which is the fundamental. You can consider a quantum as an elementary particle that is not between two interactions. Then we have the elementary particle, which is a causal chain of states of an elementary particle. And then we have the causal system in which you have a complex causal relation between all the quantum entities. So this is the very fundamental ground of the EMMO. And then we have the relation that connect the quantum entity, but also the macro entity, so aggregates of quantum, using causality between macro entities. So introducing the concept of next, so introducing a temporal interpretation of causality, or using spatial relations that are an expression of contact and spatial-like interaction. So we can, in the EMMO, we can represent fundamental phenomena like Compton scattering, Bremsstrahlung, pre-production, using representation that is quite easy to represent logically. But one of the important points is that you are not supposed, using the EMMO, to dig up to the quantum level, because what we did was to create a causal relation that apply to macro entities, so to entities that are the fusion of fundamental entities. Like, for example, you can work at atom level if you want, and say, for example, that two atoms are connected using electromagnetic interaction. And if you want to be more specific, you can always decompose an atom into the constituent, and you can declare that this electromagnetic interaction occur between two electrons in the shell of the atom. So this is so the standard model of particle is a way to deal with to provide rigorous foundation to the EMMO, but it's not required to use it at operational level. So here an example of this approach. For example, you can represent in the ontology a fusion reactor as a black box, or if you want, you can decompose. You can focus on the fusion reactor and maybe focus, for example, on the interaction between the plasma and the shield. And you can declare in the ontology that there is a electromagnetic interaction and a neutron bombardment from the plasma to the shield. Or you can focus even more, and then you can focus on the plasma and understand that there is a phenomena in the plasma called Bremsstrahlung that provides you with photon, and there is the heating of the shield coming from the interaction with an atom and a photon. These are a classical interaction, so these are described by classical physics. Or you can go a bit more into the detail, and you can, for example, want to express Bremsstrahlung as a fundamental interaction in which you have to apply quantum mechanics. So there are relations in the MMO that lets you express the fact that two entities are related using a quantum field, and then can help you can give you the hint about what are the entities that you have to use in order to build the Hamiltonian, and what are the potential that you have to use in order to generate this Hamiltonian. So just to tell you that in the MMO you can work at a very high level, also to a very low level, applying a different level of modeling. But as I told you, we don't want you to go to the fundamental level, and what we did was to create relations that brings the causality and the mereology a relation up to a macroscopic level, and then this relation takes the label of more friendly label, like for example, is output off, is input off, affects, contributes, participates, or for example, is a status, is a behavior, is a subobject, constituent, is a stage of, and so on. So what we did in CoBrain, for example, was not to bother the partners with Feynman diagram and so on, but simply provide the CoBrain partners with this set of high-level relation, and ask them to express their knowledge using this high-level relation. I will show you later how this went. So, so in the MMO you can then represent materials, knowing that it is always possible to go down, to go deep, and to provide more detailed relation and models for that particular entity. So in fact, we built upon this standard model of particle foundation, we built a material taxonomy in which, starting from elementary particles, we go up to the physical particle, particulate matter, up to the molecular entity, and then up to the material, including mesoscopic and continuum material, and also the possibility to categorize material using the particular characteristic like a function or domain or structure and whatever. So, but all of these classes are defined using axioms that connect these entities with a more fundamental theory. So let me skip through this. So in the MMO, we also wanted to be to apply this ontology to macro concept and to concepts that are not strictly related to physics. So what we did was to create an approach which is called the perspective approach, in which, given the physicalistic foundation describing the world, we provide a level, so a layer in which a user should usually live, that categorize things according to more, intuitive concept. For example, the distinction between process and object, the distinction between whole and parts, the distinction between the type of information that an entity provides, and so on. So these perspectives are perspectives that, for example, in the case of holism, declare something according to the part that needs to be present, or define the part according to the whole to which this part should always belong. The reductionistic branch is a perspective in which you can generate a hierarchy of granularity. So you can create directly rooted tree of partud in which you can represent materials according to different, or devices, for example, according to different layers. This can be useful, for example, in order also to define different level of complexity or expertise needed to deal with a level of detail of description. So in this way, if you use this multi-granular approach, you can also represent, for example, material in a multi-granular way. So, for example, you can have the mesoscopic level and the continuum level of material in which you can, for example, declare a polymer composite as made of polymer, that are made of monomer, that are molecules, that are made of bonded atom. Bonded atom are atoms that are made of nucleus and electron, and so on. So using this reductionistic approach, you can, if you want, stop here, but the knowledge base will always tell you, if you navigate the T-box, it will always tell you what this polymer means. A polymer means something made of blah, 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 and so on. So you can, so in this way, an ontology is provides you much more than a keyword. It provides you a concept, and this concept is part of a knowledge base that can be navigated, and then you can understand what you mean when you say that this entity that you have in your lab is a polymer, because it's part of a very well documented entity. So let's move through this. We also use an approach called semiotics in order to represent the properties of things. So, for example, we want to represent the process for an observer to look at something and recognize it in some way internally, and then express the information using a language that can be understood also by others. So this is called semiosis. And what we did is to apply this to all the scientific way in which we can generate properties. Because if you think about a property of an entity, it is always come from an observation or from a model, for example. So what we did in the EMMO is to build this structure of the structure in which an object, for example, a sample, is interpreted by someone, and this someone provides you a sign for it. For example, the thermal conductivity of a particular material has been obtained using this process called semiosis, but in this case is for example, experimental observation by a particular interpreter that can be human beings or also a device, for example. So in this way, we can connect an object to a particular property. So, for example, a material to thermal conductivity, and we can document the way in which this has been provided and the authority and the agent that is behind this assignment. So, if you have an entity, you can have several interpreters and several signs that can be attached to this entity. So more than one sign can be used to refer to the same entity. For example, P, pressure and temperature, or a thermodynamic system, name and nickname for a user, two different opinions about a restaurant, and so on. So in the EMMO, we have the ontological entities, and we have the properties that are the sign. You can consider the data being sign for a particular entity. So this is how we place the data in our ontology, and we connect to the entities to which they stand for. Data are represented in the EMMO using a very general approach that you can find in the from philosophers of information science. For example, Luciano Floridi in this book provided a definition of information that has been used in the EMMO to create the taxonomy of data. And what we did also was to introduce in the EMMO also a methodological system in which it is possible to express the nature of a data according to methodology. So when you have, so in the EMMO, you have, for example, your physical entity, for example, a crystal. You declare that you have a sample that it is a crystal in your lab, And then you can say that an experimentalist looked at the material sample and then provided a CIF file for it. This CIF file is a crystal model, so it is a sign for the material, and it is expressed syntactically using a CIF file. So in this way, the EMMO connects a physical entity to a particular property that it is declared by a particular experimentalist, and we generate information. And information is a syntactically, shareable entity, like for example a file that possesses a meaning. So that is assigned, that is a model for this material sample. So reaching the definition of information. Information is data with meaning. So data, a syntactical structure with meaning, so that for someone is assigned to this particular sample. So this is how we deal with, how we semantically enrich the data. So for example, you can have a material that possesses a physical quantity that as part made of a value and a reference unit, for example, and or a model, for example, is something that stands for a particular material and participate to a simulation and so on. So you can document all these activities and the data that you can generate. Let's go through the. Also, it is possible to represent workflow in the EMMO as shown here. So it is possible to create a causal chain in which you document the data input and the data output of each task, and you connect causally the two tasks, and you declare the data used for the interaction. And then you can represent the moda or the chada that you can use to represent your modeling activity or your characterization activities. So let me go briefly through this. But how to practically use an ontology? So the idea is that you should have a knowledge base, so a triple store that can host your ontology, so the rules and the action that made up your ontology, and also can contain all the information that you have about your domain of interest. So all the instances that you want to document. Then there needs to be an interface to the knowledge base. So something that helps you to interact with this knowledge base, so that the user can query the knowledge base to know what type of entities exist and what type of metadata connect to the entities. But our approach is that the actual data are not stored in the knowledge base, but are stored somewhere else. So for example, you can have here the information about the existence of a file that provides you information about a particular fluid, but this file is not part of the knowledge base, but is part of a database that is external to the knowledge base. So in this way, you can always you can map your existing databases, or you can keep your approach to data storage, and you can add an ontological description for your database without disrupting your actual architecture. So the idea is that a knowledge base should map what you already have, and the better your database is structured, the easier will be for the knowledge base to map the content of your database to the metadata of the knowledge base. So that's the idea behind this approach. The problem usually that we found is that this approach is something that spans from philosophy to logics to computer scientists for the serialization of the ontology, to applied scientists, and to engineers that are usually the one that in the end will use the approach. So as you can see, this approach is something that requires multidisciplinary competencies that should be used in an interdisciplinary activity in order to to give life to this approach and to generate innovation. This is the most difficult thing that aspect that we dealt with. So I would like to show you briefly an example of approach. So what we did what we did with the co-brain project was to, I'm sorry, but okay, was to create a template, this one, in order for the expert to declare the entities that they are dealing with. So the idea is that we want you to start to conceptualize your activities in an easy way. So what we did in co-brain was to start to declare the processes and the objects that are part of the thermal spray domain of interest. And then we ask the expert to fill this table with the definition as precise as possible of this concept, so that it will be possible for us to document this concept in a knowledge base. And then what we asked to our co-brain partners was to use this very simple relation, very simple concept, to express their knowledge. For example, that a thermal spray torch has constituent some nozzle, for example, or whatever, so that we can start to build to extract knowledge from the expert and then to place this in an ontology. And also what we asked to the co-brain partner was to create an A-box representation of what a thermal spray process is. For example, the substrate participate to the process of substrate preparation that consists of roughening, cleaning, tooling, and so on. As you can see, the substrate is participate to and is subject of different transformation that led to its final status, substrate 4, after the thermal spray, and so on. So this type of conceptualization has been used in order to define what is the process that we are dealing with, and also what are the properties in this way, in this part of the tab, properties that are related to, for example, the substrate. So we have the list of the properties and the entities to which this property stands for. Again, each of these properties has been documented by the expert in this table in order for the ontology to be very well documented. You can see, for example, here how an ontology appears in a tool that has been designed to deal with ontologies. You can see here the taxonomy of the EMMO ontology. You can see also the fact that we can navigate through the concept, and each concept is documented so that it is possible for a user, when you, for example, declare that an individual is an encoded data, you can read the annotation and then understand what this concept stands for. Again, you have, for example, in the metrological language, you have, for example, references to the documents that are used to build this knowledge. For example, here we are referring to the vocabulary of metrology. And then you have all the subclasses, in this case, for example, the measurement units. Or we can also go to the properties. Here we introduce in the EMMO the ISQ quantities, so iteration system of quantities. And then we have here the reference to the ISO quantity, and also the link to the definition of these quantities that can be used by the user in order to understand what we mean with this concept, and so on. So you can use all these concepts together in order to say something about an entity. But let me show you to conclude an example that we developed recently about how to represent and document the data, but maybe just later we'll show you a bit more. For example, let's make the hypothesis that you want to represent a task, the task of fluid density calculation, which is something that we are doing now in the Open Model project. The fluid density calculation is a task that the T-box tells us that it is an EMMD simulation, and it is a task. So you can declare in your ontology that exists this task, that this task has been performed by someone. We know also that this fluid density calculation is a functional icon, so it is a model for a fluid, that it is a material, that it is also matter, and so on. What we can express in the T-box is that the fluid density calculation of this task has always an input, exactly one data set that it is declared here, for example, that possess three data entries, and these data entries are here, for example, a pressure, that it is also a real scalar, that has a unit bar. Also temperature, that it is a real, that has measurement unit Kelvin, but also needs to have a reference, so an URI, to another data set that contains the potential data for Lennard-Jones interaction potential. And we know that this entry in the data set are, for example, the Lennard-Jones is a description for a molecular entity that is a particular matter, that is matter. So as you can see, you have a very powerful description of what your task is and how this task is related to the concept of materials and so on. If you go to the output, for example, is in this case is an entity that is a density. It is a real of type real, and it is measurement unit kilogram over cubic meter. So you have this T-box. We have declared this in the T-box of your ontology, and then you want, for example, to declare that this task has been run by someone, and provide and using a particular data set and providing this out. So what you can do is to declare this individual as instances of this, and then you can attach data to this data set. For example, that this individual is accessible in this location, and for example, that this individual has output this value, and you can store this, for example, directly in the knowledge base if you want. Another possibility is to populate the knowledge base also with this three individual that stands for the entry in the data set. Each of these entry possess a data, for example, the temperature and the pressure, and also possess the data, which is the location of the other data set in which you have stored the Lennard-Jones parameter. So you can then represent a task. You can represent the data set that are used in this task, and you can provide information about where to locate this data set. If you want, you can be very specific by also declaring the content of the data set, or if you don't want to be so specific, you can simply stop here, and then declare that I have two data sets. I know the content of the data set because I can navigate through the T-box knowing that this data set possesses this entry, but I don't want to overcrowd my knowledge base with actual data. I just want to point out that if you're interested, you can access this data set that is structured like that in reaching this location. So this is a flexible way in which you can decide to store or not to store in the knowledge base your data. And then an example of how you can use a knowledge base to map your existing data set, your existing data using the knowledge base. Of course, this what I shown, these individuals can be declared using, for example, a JSON LD expression in which you can represent, for example, declare your data set that is a description for a fluid that has access to URL dataset and so on. So this is one possibility to deal with to serialize and to populate your knowledge base with this concept. So in the end, given a T box, you can always create a context in a JSON LD file that lists the names to be used here. And then you can simply ask a user to follow a particular schema and to document their, for example, modeling activity using the entry of the context that you populated according to your expressivity ambition, so what you want the user to describe. Another possibility is also to use something like that, for example, tools that enables you to find a schema. So you can define a schema, for example, the schema for declaring a person, sorry, to declaring a person, and then you can, for example, automatize create a mask for populating your JSON LD file with the data that you need, so that people can document what they did in a very easy way. Generate the JSON LD schema and then deliver this JSON LD to the file, to the knowledge base, so that they can populate the knowledge base with the information about what has been done, what are the data sets that are connected to a particular task, where the data sets are located, and so on. So you can, as soon as you set up your knowledge base, provide the end user with a simple interface. So you can sit in your lab, you can run an experiment, you can open the schema for that particular experiment, you can fill the information, and then you create your general LD file, you can submit to the knowledge base, and then you have your knowledge base populated with your particular run, and you have documented what you did, and you have provided a way for other users to reach your data set that you stored in an accessible location or entry in a particular database. So this is it. Sorry, I rushed a bit at the end of the presentation, but this is essentially what we are doing in the EMMC with the EMMO, and what we're doing in the CoBrain project, that I hope can be also useful as inspiration for your projects.